All right, so this should be about page 238 of your workbook. This is going to be 4.6, which is applications of trig derivatives, part 2, related rates problems. And so we're just going to go through one problem in here, but kind of demonstrates the ideas of what's going on with this. Nothing really new from the last time we did related rates, in that we should still use the same processes in getting our solution down. The only thing different is now we're going to be using some trigonometry. We're going to do stuff that has change of rates of angles, which kind of makes sense because now we can find our derivatives of our trig functions. And so let's go through this one. This starts off by saying a balloon's released at point A, rises vertically at a constant speed of 5 meters per second. Point B is at the same altitude as point A, but 100 meters away. So let's draw your A is right here. B is at the same altitude. It's 100 meters away. So let's call this 100 meters. We've got a balloon that's going up from A at a constant speed. Let's call that C. At what rate is the angle of elevation of the balloon at point B changing? So there's our theta right there. At what rate is it changing when the balloon is 200 meters in the air? So remember that when we find our rate, it's happening specifically at a value of 200 meters in the air. We need to define some variables. We need to say that. So h is the height of your balloon. We have always, T is for time, is being measured in seconds. We know that it's being measured in seconds because it gives us the speed that is measured in meters per second. And theta, angle of elevation. Point B. Our units on this is in radians. And we're ready to go. We need to state that dh dt is how the height is changing over time. As it's changing, it's rising at 5 meters per second. D theta dt is what we're trying to find. But with this statement, we can't just leave it at that. Whenever we have d theta dt, whenever we have a derivative equaling some question mark or unknown, we need to state this is happening when h equals 200. May or may not be enough information with h. We might have to go further. In this case, we do. We have to say how h relates to how h relates to theta at that time. And how we're going to deal with this is we're going to realize, okay, so if this is my h in this diagram, if we've got theta over here, if we have h and 100, 100 is a constant, therefore we have tan theta is equal to h over 100. When it's 200, we have tan theta equals 200 over 100. So theta equals tan inverse 2. Make certain your calculator's in radians. We are going to use a decimal approximation of this just for writing it down. When we're actually doing some math and calculation, we'll probably use that tan inverse of 2, but it's approximately equal to 1.07. All right, so we are trying to find how quick this angle is changing. We know that this is 100, that's a constant. We know dh dt, so we have this relationship between this angle, theta, our h, and our 100. and it's easily defined as equal to h over 100. When we differentiate this, we take the derivative of this with respect to time, and take the derivative of the right side with respect to time. So d dt of tan theta. So recall that when we implicitly differentiate, when we are differentiating this with respect to time, we take our derivative of that. On the left side, we have secant squared theta, but that has to be multiplied by the derivative theta with respect to time. Whether you think of that as implicit differentiation or whether you just think of it as the chain rule that we are multiplying by the inside, which is just d theta dt, either way that works. With this one, we have h over 100, so 1/100th dh dt. In our next step, we are going to now substitute, so secant squared of 1.107 d theta dt is equal to 1/100th times dh dt, which we know to be 5. When we simplify secant squared of 1.107, that actually ends up being equal to exactly 5. So depending on what you stored in your calculator when you did your tan inverse of 2, if you do tan inverse of 2 and then cosine of that, and then square that, and then take the reciprocal of that, that should give you exactly 5. Depending on how many decimal places you hold in your calculator, if you're using your shift and then answer function on your calculator, but that should be exactly 5. So d theta, 5 times d theta dt, this simplifies to 1 over 20. Divide both sides by 5. It should be 1 over 100. So therefore, the angle of elevation, to the balloon from B, when the balloon is 200 meters in the air, is 0.01 radians per second. Okay, so there's a lot that I included in that sentence to answer this, just to kind of highlight exactly what it's representing. If you're standing at B, obviously your eyes are rotating upwards to follow this balloon, and when it's exactly 200 meters in the air, that's how quickly your angle is changing, whether your eyes are rotating up or whether your head is turning. That's the angle of rotation at that very moment. Anyway, that's all that we have in this section. So good luck. If you have any questions, please ask.